this yours? Okay, great. Everybody's back and settled in. Well, we've come to the final presentation, our sixth presentation of the afternoon. And it's my pleasure now to introduce Joshua Kubiak from the Louisiana School for Math, Science, and the Arts. And I hope I say the next part right, from Natchitoches, Louisiana. Okay, not bad for a Yankee. I'm from the north. And let me read the title. So, Asymmetric Conjugate Addition of Ortho-Quinone Methides as a Pathway to Communesin Analogs.
Hi, I'm Josh Kubiak, and this past summer I researched the asymmetric conjugate addition of ortho-quinone methides as a pathway to communesin analogs. Leukemia is cancer of the blood, or hematopoietic bone marrow, and is characterized by an increase in abnormal white blood cells. Leukemia causes hundreds of thousands of deaths each year, including several thousand in the United States. In 1993, a class of compounds known as the communesins was discovered, and has since then been a focus of research as a possible treatment for leukemia. These communesins are secreted by aquatic species of the penicillium fungus, found growing on certain green algae and sponges. They are classified as A through H, and members of the species have shown potent cytotoxic activity towards leukemia cell lines, as well as some interesting insecticidal activity. For the past 2 decades or so, researchers have been trying to create these compounds in the lab. Thus far, this has resulted in the synthesis of only select few due to the challenging polycyclic or many-ringed framework of these compounds. However, they all share a common tetracyclic or 4-ring structure pictured here. This is of interest to researchers not only because it is easier to access, because it is a common structural motif found in natural products. Similar to communesin B is nomofungin, which is structurally identical except for a slightly altered core structure containing an oxygen instead of a nitrogen. In 2010, Pathak et al., or the Sigmund group, created the core structure of nomofungin in a palladium-catalyzed difunctionalization reaction and found that derivatives of the compound cause G1 and G2 arrest in breast cancer tumor cells. However, their method is limited because it requires the presence of 2 hydroxyl groups on the substrate and also uses palladium catalysts, which are quite expensive. My goal this summer was to find an alternate synthetic pathway that avoided these restrictions. To do this, I used ortho-quinone methides. A generic ortho-quinone methide is pictured here. These molecules are highly reactive at the benzylic carbon, where they're susceptible to the addition of nucleophiles, such as indole. Through the 1,4 conjugate addition of an indole via this carbon to the benzylic carbon, an intermediate can be created, which can then be cyclized to generate the 4-ring structure at the heart of nomofungin. Ortho-quinone methides are also a good starting point because they can be synthesized from sesamol, which is an inexpensive starting material, using methods that are already well established. In my work, I used 2 ortho-quinone methides labeled 4 and 7. To create 4, I started by acylating sesamol in a Friedel-Crafts addition with acetic anhydride, here, to produce 1, which was then put into a Claisen condensation with benzaldehyde to produce a chalcone, which was subsequently deoxygenated and then finally oxidized. To create 7, I again started with the Friedel-Crafts addition, this time with 4-methoxybenzyl alcohol, followed by oxidation to create the ortho-quinone methide. It was found that the addition of indole onto these substrates occurs easily at room temperature with a simple acid catalyst. However, the addition creates a new chiral center, or carbon with 4 distinct attachments. This is a problem because when a chiral center is formed, the product is created in 2 different enantiomers, which are non-superimposable mirror images of the product, sort of like your right and left hands, and they're 3-dimensionally different. Because biological systems operate on shape-based recognition, usually only one of the enantiomeric forms of a biological molecule will be active, whereas the other will be useless. Therefore, it was necessary to create a synthetic approach that produced predominantly one of the 2 forms. Not much work has been done on asymmetric conjugate additions onto ortho-quinone methides in the past, but based on similar reactions, we hypothesized that bienol phosphoric acid catalysts could be used to control the selectivity of the reaction. Since no work has been done on this specific reaction, a set of optimal reaction conditions had to be created. To do this, I ran several reactions in small scale while varying temperature, ortho-quinone methide, indole, and the catalyst used. Each reaction was run on a 0.1 millimole or 10,000th of a mole scale. The general procedure was to take either ortho-quinone methide 4 or 7 and place it in a reaction tube along with a magnetic stir bar. Meanwhile, in a separate tube, 2 equivalents, or 0.2 millimoles of indole, was dissolved in 1 milliliter of solvent, which was either toluene or dichloromethane. And the indoles that I used were an unsubstituted indole, a 1-methyl substituted indole, and an ethyl carboxylate substituted indole. Next, the desired amount and type of catalyst was added to the first reaction tube containing the ortho-quinone methide. Quickly thereafter, the indole solution was pipetted in, and the reaction tube was capped and allowed to stir. After reacting, the product was isolated via silica gel column chromatography. The structures were then verified through proton NMR, and the enantiomeric ratio, or ER, which is the ratio between the 2 different 3-dimensional forms, was measured using high-performance liquid chromatography through a special chiral column. Here is an image of one of my conjugate addition reactions, stirring in a Dewar flask of dry ice and acetone at negative 78 degrees Celsius. By examining the mechanism for the conjugate addition, we can better understand why these catalysts induce selectivity. The catalyst is this larger molecule pictured here, and before indole attacks the substrate, the catalyst forms a hydrogen bond with the carbonyl of the ortho-quinone methide. When it does this, it effectively blocks 1/2 of the substrate by creating steric hindrance and makes it more favorable for the indole to attack the opposing face, thus generating an asymmetric product. In my first screening, I used ortho-quinone methide 4 with a 1-methyl indole and dichloromethane. The catalysts that I used were an anthracene substituted catalyst and a triphenylsilyl substituted catalyst. At room temperature, neither of these created any selectivity, as indicated by an ER that was near 50-50. When cooled to negative 40 degrees, there was slight improvement in the reaction using the triphenylsilyl catalyst, which indicated that cooling the reaction further may increase selectivity. This thought was also supported by qualitative analysis of the reaction. As the addition occurs, there is a color change from red to pale orange, and with cooling, this color change occurred much more slowly. Therefore, we could see that cooling was slowing the reaction down and allowing it to occur more selectively. So my further screenings were run at negative 78 degrees Celsius. This time I am again using ortho-quinone methide 4 with all 3 indoles mentioned in both dichloromethane and toluene. This time I am also using an unsubstituted catalyst and a dibromo substituted catalyst. However, none of these combinations produced a selective result, so I moved on to ortho-quinone methide 7. This time, running the same set of reactions, there was clear selectivity achieved in the addition of 1-methyl indole using the dibromo substituted catalyst in both dichloromethane and toluene, with the highest ER of 37 to 63, which indicates that one of the 2 forms was produced almost 2-fold as much as the other. I then took the most promising addition product, which was 8A, and attempted 3 different cyclization methods to form the tetracyclic structure that I was looking for. I tried oxidative cyclization with tert-butyl hydroperoxide, oxidative cyclization with N-bromosuccinimide and pyridinium p-toluene sulfonate, and finally an acid-catalyzed cyclization using p-toluene sulfonic acid. The second method, using NBS and PPTS, produced the desired tetracyclic core structure, which is identical to the core structure of nomofungin, with the presence of this additional double bond, which will be discussed later. In conclusion, I found that the selectivity of the 1,4 conjugate addition of indole onto ortho-quinone methides can be controlled using chiral bienol phosphoric acid catalyst. The product of such an addition was cyclized to create an analog for the core structure of nomofungin, which is again similar to the core structure of communesin. This analog was created totally in a procedure starting with sesamol, which is again a relatively inexpensive starting material, and using a method that avoided earlier restrictions. The generated core structure can be used as a scaffold to create novel compounds which may have activity against tumor cells or other useful effects. I also created a set of optimal reaction conditions for the conjugate addition. The reaction should be run at negative 78 degrees Celsius for at least 6 hours, using dichloromethane as a solvent because it gave consistently higher yields. 20 mol% of a bienol phosphoric acid catalyst should be used, and it is crucial that this catalyst have large substituent groups to help increase hindrance when it is blocking half of the ortho-quinone methide. The indole used in the addition cannot have too strong of an electron withdrawing protecting group, or the addition will not occur, as was the case with the ethyl carboxylate indole. And finally, the ortho-quinone methide needs to have directly attached bulky substituents near the point of attack, as 7 had an aromatic ring that was much closer to the point of attack than 4 did, and only 7 resulted in selectivity. In the future, I would like to design and test other catalysts, including taking a look back at the triphenylsilyl substituted catalyst, which showed some minor selectivity even at negative 40 on ortho-quinone methide 4. I would also like to try additional cyclization methods, including using DMDO and a weaker acid. Both of these methods would potentially reduce that additional double bond mentioned earlier. The absolute stereochemistry of the product can be determined through X-ray crystallography, and the proposed mechanism can be confirmed using spectroscopic methods. After this is done, derivatives of the substrate can be created and run through bioassays to determine if they have any useful activity. I would like to thank Boston University and the Schaus Lab Group, including Dr. Scott Schaus and E. Luan. I would like to thank the faculty of the Louisiana School for Math, Science, and Arts, including Dr. Mark Ward, Dr. Christopher Hines, and Dr. Allison Landry. And finally, I would like to thank Siemens College Board and the George Washington University for giving me the opportunity to be here today. Thank you.
So we're going to deviate a little bit from our procedure of having the Q&A immediately after the talk. Since this is the last presentation, this is our last opportunity to address the audience here. So one thing I'd like to do is just to reflect back and comment on just the outstanding presentations that we saw, Josh's and everybody else's. Everybody in the audience today learned a lot, I think, about diverse topics from mathematics to bioengineering to astrophysics, biology, chemistry, and biochemistry. So we had a very diverse range of presentations today. And so I'd like to ask all the Siemens Competition national finalists to stand so we can recognize you and just give you a great round of applause. Very well done, very impressive, thank you. And then I also would like to thank the judges for their service. We've been having the Q&A sessions, and we've been having some great dialogue, some great insightful questions to probe deeper into what's been presented. And so I'd like to also ask the judges to stand and face the audience and give them a round of applause. Thank you very much. And finally, I'd like to turn over the podium to Jennifer from the Siemens Foundation to give us our final remarks here. And then, Josh, we will go and do your Q&A right after that.
Thank you, Michael. So again, we'd like to thank all of you for attending the presentations today. As Michael indicated, we thought they were phenomenal. You guys did a great job. We are going to now conclude the program, and we will have the parents and our guests who have coats upstairs in Hippo on 5th floor to go up and get all of your belongings. Our buses are here, so we will transfer you to the buses and take you back to the hotel. Once we get to the hotel, we will be leaving to go to the Mellon Auditorium for tonight's recognition gala at 5:45 p.m. The bus will be leaving at 5:45, so we're going to ask you to be in the lobby downstairs in your black tie and fancy apparel at 5:30, and we will transfer you to the Mellon Auditorium. And our logistic experts, Kamisha and Marcus, will be there to greet you, get everyone on the bus, and our guests that are not going with us tonight, we hope to see you tomorrow morning at the press conference, which will start promptly at 9:30 a.m. here in this same theater, and we'll hear the order of the scholarships for the students on tomorrow. So with that, good night, and we look forward to seeing you soon.